Hello and welcome to another episode of Learning Rust with Git Oxide. Welcome back, Sydney.
Hello, thank you.
And today we're going to talk about a very exciting topic. Exciting probably because it's kind of confusing initially, and it also is kind of related to Git Oxide, but in an inverse way, by not being there in many cases. I'm talking in riddles, but what I really try to talk about is strings. Seems easy. Strings. I mean, how do you know strings? What's strings for you?
Well, coming from JavaScript, TypeScript, it's just a string. It's simple. You just use it. I don't know. There's not much to say about it there, I guess.
Strings are strings. So
Yeah.
you put images into strings as well.
Mostly characters.
Mostly characters. Okay, so we have strings contain characters. And characters, that's the letters that you write in the alphabet, I suppose, or is it something special?
Well, I mean, it's basically in TypeScript, there's not really a character type like in Rust, right? It's just a string with a length of 1. So it's any symbol, anything that I have on my keyboard, an emoji, it's just one character is a string with a length of 1.
Okay, wow, that seems like a lot of memory goes into each of these then. But yeah, makes sense. Keep it simple, I guess. Rust also has that notion, but yeah, let's dig in. I promise that we show where there are no strings to start with and have a reason to look at the documentation here of Git Oxide. This is the Git object crate. And there's the typical objects that we all know and love, blobs, which is just a bunch of bytes, and commits and tags and trees. And I think commits we all know kind of best intuitively at least, because yes, we all do commits every day. And if you look at this commit object, for instance, this is an object that owns all its fields, hence there is no lifetime here. Then you see that things like the message that says it's a string, but it's also a B string. And a B string comes from the B string crate, or B str crate, I don't know how to pronounce that properly, which means it's not a standard library string as you use it usually in Rust, but B stands for binary. So it's a binary string. And it's kind of strange because you would expect, anybody to just use strings because strings are characters. And when you type a message, the message is just a bunch of characters on your keyboard, right? Like, why B string? Why binary string? That makes no sense. Obviously, that needs a lot of work still. Or not. So what we would have expected, maybe, because it's owned, we have this capitalized string thing, which is a Utf-8 encoded global string. Okay. And in theory, you could just put, remove the B, then you have a string here, and that can also represent a message. And it probably can represent any message, right? So why the fuss about B string? What do you think? Like, why would you make that differentiation?
I'm not sure actually. Like, is there an efficiency gain or advantage to that, or is it just easier to use coming from a crate?
Yeah, that's super interesting points. Like, is it just easier to use because that crate might have a different API that makes it easier to edit strings or deal with them in some way, or more efficient? Efficiency, I think that's definitely a point, even though I didn't choose that. Like, I'm just implementing something that can work with Git repositories. So somebody chose that, but the people who wrote Git initially, they chose that it's just binary data, the message. There's also the possibility for an encoding here. So you can store the encoding. And now we kind of have a relationship, kind of some connection here. Because here we have also the word encoding, right? So Utf-8 encoded string. Whereas here the encoding is just some B string again, so it's some identifier for an encoding. So now maybe it's more clear why that is, which I leave to you to kind of spell out.
Actually, I'm still not entirely sure what you're getting at.
So the encoding in Rust, it's statically known to be UTF-8. So whenever you have a string of any kind, so anything that lives in std string, then this thing is UTF-8 encoded. But here in Git, the encoding is undefined. If it's none, then you have to figure it out as the one who pulls out these bytes, or it's defined to be something. And there's a bunch of different encodings in the world, especially pre-UTF-8, pre-Unicode. Sorry, UTF-8 is an encoding for Unicode, right? But pre-Unicode, what happened before Unicode? There was a ton of different encodings. That's what. And, you know, Korea, Japan, China, they all have their own kind of code pages essentially, and they're all incompatible, and you better know what kind of encoding you see in front of you, because otherwise you get funny characters at best and gobbled messes at worst. And that's why. So in other words, this is B strings because strings can't represent everything that Git might throw at you, and that for Git is valid here. It's an encoding.
So it's compatibility, basically.
Yes. Because if I wanted to have a string, I can create one, but look at this. String from, you have these from functions here, methods, from UTF-8. And this returns a result because that could be invalid UTF-8. So if I would read bytes from Git, that is, Git says that's the message, then I would have to try to decode it as UTF-8, but that may fail. And then what? Then you ignore the message? Well, there's other ways. There's Utf-8 Lossy. So that just puts this unknown replacement character kind of thing into your byte sequence. So whenever it's invalid UTF-8, you get this funny little question mark. And that would work, but also then you degenerate information to the point where maybe it's all question marks because it's just some crazy code page that makes no sense as Unicode, maybe. And it's probably possible. At least it's totally gobbled. And that's that. So strings simply can't, or Rust strings simply can't represent what Git considers a message. And it's fair that Git doesn't impose any restrictions, because sometimes Git simply doesn't know the code, the encoding. Also, it does not care necessarily, because it's just a matter of your terminal configuration or whatnot and your personal configuration, unless you specify the encoding, which you can in various ways as well. But then also Git usually does not care about the encoding. In most cases it doesn't, but it's something that other programs can extract and then use to know how to decode the message. And that's Git versus Rust in this case, and this is why bstring is so handy. It still gives you a string-like API, but it knows very well that what you try to do there might simply not work because you work with bytes, and intrinsically, if you use any kind of these byte-based APIs, you assume ASCII essentially, because if you type any kind of string here in Rust, right? If you want to use an API, then you can have a binary string. I think we did that before. But this is literally just, this doesn't change the encoding at all. You know, this is not magically something else. Still, the byte value for W is the same as it was before, but now you have a different type. Now you just have a bunch of bytes, whereas before Rust knows it's Unicode encoded, or it's UTF-8 encoded. So inherently, UTF-8 gives you ASCII for these standard characters, and all the other code points in Unicode are then encoded differently. But Utf-8 has a bunch of nice properties, which is why it's basically backwards compatible to US English, right? And that's kind of the baseline for historical reasons. But above a certain code point, so to say, or above a certain value, you can then encode all the other 3 million whatever code points that Unicode currently entails. So that's Unicode. All right. I think that could be it. I mean, I think that's all there is. Sometimes use sometimes use strings in Git oxide, but for most of these types, you simply don't have that luxury of knowing the encoding. But yeah.
That's all that bstring does. So basically you work with it like a normal string, but it's just the underlying encoding that's different essentially from Utf-8.
Yeah, it's unset. Like bstring does not have any encoding. And you use it like a bag of bytes. And this might be, you can say strip suffix, strip prefix, like things you usually do. But inherently, when you choose the byte sequence to operate on, like what do you want to strip, you type it in as a binary string like here, right? And then the byte sequence you get is UTF-8 / ASCII. So you kind of still have a preference, but that just means that maybe your stripping doesn't work because it's actually something very else in there. But still, you can do it. Whereas with an UTF-8 encoded string, you first need UTF-8 to be able to do anything, which might just not be the case. So that's that. So bstring does exactly that, gives you the string-like interface, even though doesn't assume any encoding, which is super useful. Also for display, by the way, like for debugging this stuff, when you want to debug print something, if you just have a stack of bytes here, you see numbers, and that does not help because most of the test data, of course, it's just ASCII, So you just want to see that. And bstrings, they just assume Unicode, but they don't enforce Unicode. So on display, they try to display Unicode, UTF-8, basically. And if that works, good. Okay. Otherwise, question marks.
So that means you would never need to really convert these things into a specific encoding unless you want to display it, which then it assumes ASCII or Unicode essentially. But otherwise, you're always staying in this unencoded world and passing these sack of bytes around essentially, and you don't worry about the encoding at all.
That's true, because you really do not have to worry most of the time. But those who display, they then have to worry, and bstring makes an assumption which usually works, which is good enough for debugging. But other applications, they might want to do better than that, I suppose. But they can. That's the good thing. They can just do what they want with this sack of bytes. Just for completeness, this is a commit ref. So it's the same thing as before. It's a commit, but this time most of the data is not owned anymore. Most of the data is just backed by some other buffer of sorts. And these are essentially pointers into that buffer. We reference portions of that buffer. So bstr is the same thing as a bstring, but is not owned. It doesn't have its own back buffer. It doesn't have its own vector of bytes. It just points, it's just a bunch of bytes that it points to. And that's that. That's a bstring. Let's see if we can see how this is implemented. Yeah, look at that. So a bstring is really just a bunch of bytes, a slice of bytes. And there's not even a slice of bytes here. This is a bit, it's, somebody really knows what they're doing is implementing this and bends some rules, uses some unsafe to turn a slice of bytes, which is actually a slice because you see this borrow here. That's what you want. But these standalone things that are like arrays, but don't have a statically known size, that's something that doesn't really exist. Like, it's amazing that you can specify that, because that is not, like, it's not a thing. But it never really is a thing, because that only ever exists as a borrow. You see here, it's just reinterpreting, transmuting byte slices into a B string, which allows you then to use it as a B string, or to transform it back into a bunch of bytes. These transformations are free, essentially, right? They're just a different view on the same memory, and this is why that works. But underlying bytes are really just a byte slice, which makes this basically free, right? Like all these transformations, they don't cost anything. And there's also a nice property of B string that it's done like this. So you just have a different representation of a different view on these bytes. And that's exactly what you want. Yeah. So there's two kinds of strings, I think. So what I'm trying to show here, there's a B string and a B stir. And this difference is really just about the starts that comes with it. So a B string has a vector, whereas the other one has a slice of bytes. And now it comes. There is a one-to-one relationship to standard library strings and stir slices. And they're exactly the same conceptually. So this one here, the string, does have a bunch of bytes that back it, but these bytes are known to be Utf-8 encoded. And that's the difference to B string again. They don't have an encoding. But here it's validated. So once you have a string, you know it's valid Utf-8. And when you look at, where do I find it? As stir, then you see you can just represent yourself as a so-called string slice. But this string slice, it's just a fancy way of writing that it's a borrowed bunch of bytes like before, where you know that this is Utf-8 encoded. So it's a borrowed bunch of bytes that are Utf-8 encoded. Let's see if we can see the definition here somewhere. I don't know, actually. Can I just jump there? Let's see. I never tried to see the definition of the string slice. It must be in there somewhere, but probably it's hard to find. Maybe IntelliJ can help with that, but I don't know. Let's try. Let's try once. Can you go there? No, it's kind of too built in, maybe too built in. Maybe some compiler magic happening there that's not really defined anywhere. It's just something the compiler knows. Who knows? I don't know. But this conceptually is this. Oh, sorry, U8. Like that. And you see that actually works. Like I just put a B in front, and now it knows that this byte array should become a byte slice. No encoding necessary, no encoding predefined, but the original encoding is of course Utf-8. It just doesn't matter here. And that's that.
That makes sense, I think. I was wondering why Rust didn't do it the B string way from the start, essentially, like giving it no encoding as a default. But I'm guessing it just makes it a lot easier, and Utf-8 is usually what you use or end up using nowadays. So I get that for like being or moving towards the future. But yeah, you sometimes need that blank layer for backwards compatibility.
Yeah, definitely. And that's what B string is there for. I think that's the default. And I must say that I trust Burnt Sushi a lot. That's the author of Beaster, the Beaster crate. Also the author of ripgrap. And ripgrap is probably something that is well known by now, also outside of the Rust community, as the fastest grab thingy out there. So he knows strings for sure. So I thought, yeah, that's great for me too. I trust that. It's interesting that you say it, that, why not choose the lowest level, right? A bunch of bytes. Why even say, oh, it's UTF-8 encoded? Like, how do you know that this is actually future-proof? Right. Yeah. I think Unicode as a standard is just embraced by the world now. So in that case, it's already more widely usable than any other encoding. So correct, but then it's the encoding. Sorry. Difference between encoding and kind of, I don't know how to say that. Unicode as a code. And yeah, the encoding and the representation. The representation of the encoding. Maybe. Okay. So why not choose UTF-16? Why not choose UTF-32? I wonder. Why did they not do that? And I think it's just efficiency. Like Windows or .NET, they have UTF-16 bytes. So each code point is at least 2 bytes in size. 16 bits. Okay. So doubles the size of strings. And that easily, that is measurable. That changes your memory footprint. And you can't go below that with UTF-16. There's no way. It's kind of, for standard ASCII, it's always kind of unused, one unused byte. So English text is not well represented in UTF-16. And there's different character ranges that fare better in UTF-16, for example. And there's studies about that, actually, that say, okay, UTF-8, UTF-16, UTF-32, because they all have their different trade-offs. And overall, UTF-8 actually fares the best, given a set of trade-offs. But overall, it's just the best rounded one, with the nice property that code, and that's the killer application to me, code that expects ASCII can handle UTF-8 encoded stuff. So the standard C code that just has a char pointer, which is just a byte, that does, tries to find some characters in a string, can handle UTF-8 encoded blobs. If you put a Chinese text in there, probably, it will still find slashes, let's say. If there's some path slash separated because you don't change that, then it will still find these. And this makes this code operational. And I think that's the beauty of UTF-8 encoding. Whereas UTF-16, not so much. So from C interop standpoint, UTF-8 is also great. So no doubt, it's a good choice, and certainly a future-proof choice, and better than just assuming no encoding, because there is always an encoding, which is at least US ASCII, which is a step backwards. If you just say, okay, we can do that, but please, no Chinese. Ignore. Just they don't have computers. Something like that. And all that, of course, doesn't really work in today's world anymore. So then, how do you work with strings? Let's see. Let's start with this string slice here. And can you imagine a property of this string slice?
I mean,
just by looking at this shared borrow here.
Yeah, it's probably not going to be mutable, right? It's kind of static. You cannot change it.
That's true. That's exactly it. We can try that. I mean, we can try. Let's see if we can make this mutable. And it's not. I mean, this is just syntactic sugar, right? That's syntax for making a string slice, a static string slice to be precise.
Okay.
But there's no sugar for making a mutable one. There is no such thing, which theoretically is possible, by the way. You are allowed to change the memory that is backing this, even static. The compiler can do that. It can just, move it somewhere where it can eventually be changed, even though it's still a limited memory region. But Rust doesn't have that. And probably Rust doesn't want that, because then you can, yeah, I don't know. It's probably one little override away from accessing memory that you shouldn't access. I don't know. It's possible, but Rust simply doesn't have it. Probably there's better reasons not to have that. So yeah, these are immutable. And that's that. They don't have to be static though. So this has the static lifetime that I just don't have to mention. But this is the full type of it. Because known at compile time. Makes sense. Mm-hmm. It's just there all the time. There is no lifetime. It's just there.
Yeah.
So then, how do we access bytes? Let's make this a bit more fun. Okay.
Can you just turn that into an iterator? Does that work?
Okay. For do know in s print line. Okay. Okay. Doesn't like into iterator here apparently. Okay, interesting. Into IDAR is not implemented for string, so it doesn't just do that automatically. So also Rust does not know how to iterate a string. Not only I don't. And there's no IDAR function either. Interesting. Gets more interesting. I mean, it's kind of new to me. No, I never really explored it like this. So what you think should work does not work. Okay, what's next? Ah, there's as bytes. Okay.
Right.
And there's bytes, so that's a bytes iterator. Both should do pretty much the same thing.
So, okay. That's the special, okay, so it's a converter essentially. It just as a function that does this exact conversion for you.
Uh-huh. Oh,
kind of.
That's interesting. Oh yeah, sure. I should print the null maybe. Not the string. All right, so here we've got a bunch of numbers. 104, 101. So 2 times 108. So 108 obviously is the L. Let me close this. Huh. Why does this disappear now? Okay, that's better. And then 108, 108, hello. And that's interesting. So 4 bytes are needed to represent this sweaty smiley here. Okay. Well, that's fine. But how do I do how do I work with that at all? I can't really do anything. And it's not even characters anymore. It's now numbers. So I want something that prints correctly.
Yeah, I mean, I know you can convert these numbers to a character, right, or to a char. But I don't really know what happens with those 4 separate bytes at the end if you do that.
Let's see. Yeah, here. So we have a char type that is a primitive type like U8. And apparently we are able to say we have a few conversions here. So apparently I can convert it from a U8. So let's try that. So that's now a byte, we know that. And let's see if that works. It doesn't hate it too much. Okay, interesting. So now we have some characters back. Hello.
And 3 empty ones.
Yeah, looks like it. It's kind of, I mean, a bunch of empty ones for sure, but 1 character prints. That's nice. A funny O. Kind of close. I mean, it's a smiley, right? So there's some fun in that O now. It's not too far off. Not too bad. But also, we definitely lost information here. Seeing it like bytes doesn't seem to work. Okay. So there's chars as well. Byte. Char. So look how I now override or shadow the name of a primitive here. Char is actually a primitive.
Oh, wow, you're right.
Yeah, look at that. I mean, that gets highlighted differently, but not anymore. Now there's no char primitive anymore in my loop, but that's fine. Rust says it's cool.
Really? So that actually overrides the type if you do that?
Does it override it? I'm pretty sure you can still dig it out of std somewhere, but I've never done that. I don't know where it lives in std. But yeah, you can definitely. And now it prints correctly. Look at that here. So the sweaty smiley is still there. So it seems char is everything you need. Apparently, it can represent smileys like this. Let's see. Can I do some more magic here? I do, I try to press different characters here. I mean, on OS X, it's always so hidden. Different things happen when you press different buttons, but here, not so much. So I wanted to find the skin colors.
Oh.
And
I think you have to look for like the thumbs up or something like that. They have skin colors, but how you access it, I'm not actually sure.
Okay. Okay, so there's not so much I can do here. There's no skin color here, really? Color. I do have colors. I think they also matter for the skin color. So different skin tones, they also come with a color identifier as far as I know. And sometimes it's displayed like this, but
yeah, like yeah, that's true. So maybe just paste the color behind it. That probably won't convert it.
That would be funny. Yeah, I mean, if it can display it like this, then either IntelliJ can't properly display color coding in emoji, which might be the case, like editors are hard and stuff, but also it might just not be the right way to do this. Okay. There probably are also emojis that are so complicated that there are, or modifiers that simply, will do what I want them to do. Let's quickly search for this. macOS emoji skin tones. How do I do that?
Oh, okay. The faces have it. There's a bunch of faces, and then it displays the different skin tones automatically. So the thumbs up doesn't have it apparently.
Oh, but it does. It actually does, I think. I thought.
That's what I thought as well.
Okay. So what do they do? Click and hold. Okay. Sure, that's the thing I did not try. So I click and I hold and hold and hold. Okay, thumbs up doesn't seem to have.
Oh yeah, that works. Okay, for me at least.
Okay, so maybe I need to use a trackpad here. Or force touch. It really doesn't work for me. What's up with that? Hey, that's a bit. Oh.
That is strange.
Yeah, now I would love to just take it, copy, paste it from the text here in a browser, but they didn't put it into their text at all. Okay. Skin tones Unicode. So maybe I can take it from here somewhere. Unicode.org. Ah, yeah, there we go. And it displays something.
It's just about this.
Let's copy
Send
this.
it to you in the chat as well. Yeah, you can copy it.
Okay. Oh, it did not copy the skin tone, did it? Okay, let's make it more obvious. Okay, there we go. Okay, now we have definitely a bunch of different skin tones there. Ah, wonderful. There we go. So it's emoji plus color. Emoji plus color. This is in our characters here. So now we lose information again, right? So we can't, whenever we can't print out what we see here as individual characters, we lose information. And there's more just like it. I mean, do I have different keyboards installed here? I might not have it active because it was so useless to me. But I would be able to write a few things here at least. Let's try. Yeah, Unicode is fun, definitely. It's kind of its own adventure. You can get totally lost in it. Now, ni hao. Is this fully encoded per characters? Yes, it is. What about more complicated stuff? Like Chinese traditional. That should be more complicated, no? But there's so many code points that it probably also doesn't matter so much. And now, that's my first ni hao. Okay, so that is entirely different in typing already, so stuff is very weird here for me. That's amazing. Okay, so these seem to print properly as well. Okay, so there's no easy, oof, yes, okay, now everything goes nuts. Quick remove. Okay, but ni hao I can at least do. It's quite amazing to type Chinese. It's not even that impossible. It's actually pretty easy. If you know the characters, you can definitely type it, but if you don't, yeah. Anyway, that's another story. Then we have at least a few of these that don't represent anymore, and that's usually called graphemes. So multiple Unicode code points, they become a grapheme, and that's what you have to treat as a unit. And there's probably more about that I don't really know or that I forget. There's lots of complexities about Unicode as well that makes you think, okay, let's have Unicode 2.0 where we fix these mistakes and break compatibility. But yeah, not so much. Not yet, anyway. Yes, and a char, if you look at this, what is a char actually? Let x be the char. Then we see it's literally this char type, and we can even print the size of a char just to see how many code points it could hold, right? So is it 16-bit? Is it 32-bit? Let's do that. std mem size of char. Now we see it's 32-bit. And that makes sense. It's like Utf-32, which is the highest possible encoding. Then you can represent how many characters? Oh, that's interesting. Wait, what? That is unexpected. Char max as U32. Because that is now a code point, just as a char, and it tries to print as a char, and that's obviously not so common to print that highest code point. Oh, that is interesting.
It's a weird number.
Yeah. I mean, that definitely is something related to Unicode. I thought it was 3 million, but it's just 1.114 million. Okay, cool. That is unexpected. I thought actually it was just U32 max. Unlike U32, which is this. This is a number I expected.
That's a lot more.
Yeah. So that's good to know, because with 32 bits you can totally do this much. So we can create lots of new languages with lots of new alphabets and characters, no problem.
Yeah, but that makes sense. I think I remember that you have you lose certain bits because they need to be kind of the actors' flags to know if the next bit is set and stuff like that. So obviously you lose a lot of volume.
I don't know. This just means this entire range is sparse. Like, this is not encoding anymore. Like, code points can be fully represented as U32. Like, U16 is too small, but once you have a code point, you have the thing that is in the code table of Unicode. And then there is no bit set anymore to say, oh, but this is, I mean, they use this. Yes, they use that. There's sometimes bit ranges or byte ranges. I don't know, certain things that are easy to check in code. But I think you can do more. Like, what's the theoretical maximum amount? Unicode maximum characters. Loss for 70 planes, each possible code points. This gives a total of... Okay, never mind.
One more than displayed here.
Yeah. Yeah, that's the max, so this doesn't count 0. So 0 to this, it's that
All
range.
right.
Makes sense. Okay, so I take that back. I take that back. So it's organized in a way that actually has this limit. So 32 bits there are. Yeah, I take it back. What I thought to know, I didn't actually know. So. Nice. So there is a limit, and with each new emoji, we eat up a character here until we eventually run out, and then let's see what happens then. Something like year 2000 bug or something, where we run out of Unicode code points. Yeah, and that's that. I mean, you work with Unicode usually with crates that understand graphemes so that you can do this correctly. But you have to be Unicode aware, and Rust forces you because it doesn't even allow iteration. And just so that we see that once, it is totally possible. Like, what happens if I slice into this string? Can I do that even? Let's see. So I have my string, and I take the first 4 characters, right? Does that work? It does allow me to do that. Okay, sorry. Let's go. Let's have a bit more. I'll leave this. Hello. Okay. What about 6? So that's byte-wise, apparently. Or is it? Maybe it's character-wise. I don't know. So character-wise, that would mean that it has to do a lot of work here, because now it has to see that the byte is not a complete code point, and then it has to do more. So that would be slow here. Okay. And there is a panic. So it does boundary checks. It doesn't only do checks of the boundary of the slice itself, which it is inside, right? This has more bytes than 6. But it also verifies that it doesn't give you slices that are not valid UTF-8. Because the guarantee of this slice operation is that you get valid UTF-8 still.
I mean, that's pretty cool to know, right? That it actually checks that for you. So you really can't do anything or much wrong with that. But it's also, I'm guessing you don't really want to work with strings like that. Like, you probably always want to do it on a character level or even grapheme level.
Yeah, exactly. You can't work with strings like that. They just don't work that way. Don't try it. It's wrong. And Rust tells you by panicking. And of course, you can always use get. So get is the same thing, but returns an option. And right now it's an option, and I can debug print it. And that's none. And this should be an option of a string slice that is hello. See? So the same thing, but a bit safer. If you must, you can. But you probably don't want to. See? It's so silly, even the baby laughs about that. And she's 13 and a half months. So we don't want to do that. Oh, what happened? Yeah, right. I should probably put an ampersand up front so I don't actually get a slice. Okay. So this also means that if we take valid slice or valid UTF-8 ranges, we can slice it so that we can get these characters. Okay. But we also saw that iterating over a character, over chars, is always working, even though you might still get the graphemes wrong. And yes, splitting over words in UTF-8 or Unicode, also something you need a crate to do.
Yeah, that was just about to say. So anytime you want to do some bit more advanced stuff with strings, then you would usually use a crate because there's no easy or good way to do this in standard Rust.
Yes, let's see. Does it have words? Can it do things? It can't do many things, really. It can strip prefixes, suffixes, real basic stuff. You can also change strings by using certain functions or methods like. Oh, interesting. It doesn't actually offer them here because it's not yet owned. But once you have an allocation that can grow, now you can push characters or push strings to let it grow.
The to owned, does that convert it into a string, like into a big string? Like
into a capitalized string? Yes.
Yes.
There's also an equivalent which is toString, which might make it easier to see what you're doing. I think it shows you the way of thinking, you know? Like I think in terms of ownership, and others might think in terms of, oh, I want a string, not a stir. But the benefit of toOwned is it works everywhere. Whereas toString is very specific, that can work, but also it always gives you a string. And it can also convert types that have the display trait implemented. Here it's a trait, see, toString. And toString is automatically implemented by every T that implements FMT display. So if you are able to display your type, toString is implemented for you because you don't need to do much. You know, you just format the thing, and this is kind of the internal way of doing it. Allocate a new own string, get a formatter, give it a buffer. This is something you can't do yourself, by the way. These things, I think this constructor it's public. Okay, never mind. You can do it yourself. And then you just display yourself because you implement that. So toString also works in many cases, and it does exactly that. Give me a string representation of yourself. That is for display, essentially. And toOwned gives you something that you own, hence you can usually modify it because it's not a shared borrow, right? And this is how I think in terms of modification, and toOwned does that generically. Similarly, generically. So types that have that implement copy or clone, they have toOwned implemented as well, automatically.
Yep.
Which kind of makes sense, right? You can usually also say clone, but it's not the same. So if you clone a shared borrow like this is, then you just clone the borrow, right? You have another handle to the thing, and you can read it and do stuff, but you can't change it. That's why you want to own it, which is interesting to see that distinction and see how it how it actually works, you know, in real Rust. Yeah, and that's that. I mean, if you put a character on here, that's the, see the difference here, single tick versus double quote, single quote versus double quote. So that's a char.
Oh, yeah. Okay, I was just about to ask. So you would push stirs onto a string, but no, you would obviously push characters onto a string.
Yeah, unless you want to push stir, then you can push string slices. Of course, the slice could have just one character, why not? But that's the distinction. And I think this is a nice segue back to TypeScript or JavaScript, where every character is always just a string of length 1. Length 1 of what, you might ask now? What kind of encoding? Is it bytes? Is it 32-bit chars or what? Really, what is that? And I'm interested to see that. I mean, why not? Ah, okay. See, that's a statement. Okay, so I don't have that installed here right now. Apparently, I haven't had any good use for that in a while. Sorry, my bad. Usually, I have Node available. But yeah, this is it in a nutshell. And sure, you can read the API and do stuff with strings, but it's very basic. And I think what you usually want to have is Unicode. Yeah, let's just say start with Unicode segmentation, exactly. And that does exactly this. You can get the graphemes of things, and you can have words and split across bounds and kind of do some basic analysis of what you are seeing there. And probably even that is full of pitfalls and things you have to know to do that properly. Yeah, don't implement your own editor unless you really mean it, I guess. Yeah, interesting for sure, and fun.
Yeah, that really shows you how complex strings actually are. How much is just hidden away when you use simple JavaScript. You just don't worry about this stuff.
Yeah, and how often, you know, like most code written in one side of the world simply doesn't work properly with input from other sides of the world because it makes all the wrong assumptions about date, addresses, like, yeah, don't make any assumption about this, and keep it as open as possible, because yeah, unless you know that you're only going to be working in Germany, then why not? That's probably going to fall someday and bother you, bite, so to say, come back to bite you. Yeah, that's all I know about strings and Unicode and encodings. And maybe one wise word: just don't use Python if you want to write software that has to work with all different kinds of inputs. Probably a lot is better now in Python 3, but it's just a great mess, and I don't understand it anymore, and I just wouldn't encourage to do that. But I'm probably wrong, and I just don't know, but it's all quite terrible. And Rust is nice, and it just doesn't hate you, you know, all the time. And this is why I say that. Like, it's an incredible difference between different languages. For example, some really kill it in the sense of they work well, and some just don't work. And I don't know if they ever get it right, and it needs a lot of tuning until it's right. And Get Python, for example, does suffer and still suffers from this, and there's just no way to get this right. It's just broken systematically, and all the transitions the code made from Python 2 to Python 3 and compatibility layers, part of it is probably still in there. And it just makes the wrong assumptions by trying to convert a string all the time and not working on bytes all the time. And that's exactly where it breaks in many places. Sometimes even during I/O, like reading from a pipe, it can break because even Python applies some encoding there if you're not careful. And that's the thing, it's all just so whoopsie, now we try to decode stuff and you didn't know, right? Because it's not really obvious. But it's okay, it's Python. We throw an exception in your face. Don't you worry. Your program doesn't do the wrong thing, it just stops working. Which is similar. Yeah. So it's this controllable versus uncontrollable. And I mean, it's probably also this conversation about exceptions versus no exceptions. And panics are supposed to abort your program and that's it. Whereas exceptions are, an entirely different way of handling errors in a program, which to my mind doesn't work if you want a program that works consistently and is understandably working. So also that Rust does properly. And I think in conjunction with strings where stuff can go wrong, we saw that. You want that. You want to panic and know I communicate errors by throwing exceptions in your face. You want the type system to handle that. And that's what Rust does. And that makes it possible to actually write code that works with encodings or in the absence of encodings, no matter what, because you're forced to deal with it. And that's just very nice, also in comparison. Just saying, it's if you're dealing with this and you don't like it in your current language, then really maybe it's the language, maybe it's systematic, and then there's no use to fight the system. Just burn it down and use something else. Anyway, go to Rust. Yeah, and I don't know. I know how this sounds, but it's just my personal experience that once you notice that some get it right, then why bother with the ones who don't? And spend time. Some have to, but if you don't, it's okay. Okay, never mind. That's it. Enough Rust Strike Force or whatever that is called, and I hope to see you around next time. Thanks for watching.
Thank you very much.
Bye bye.